Carboxylic acids can be prepared by several different methods. Oxidation of primary alcohols and carbonyl compounds. Oxidation of alkyl benzenes. Carbonation of Grignard reagents. Hydrolysis of nitriles. Hydrolysis of acyl chlorides and anhydrides. Hydrolysis of esters. Let us see how carboxylic acids can be prepared from primary alcohols and carbonyl compounds. Primary alcohols or aldehydes, on oxidation with oxidizing agents such as acidified or alkaline potassium permanganate, acidified potassium dichromate or chromium trioxide in sulfuric acid, gives carboxylic acids with the same number of carbon atoms. For example, 2-methyl-butan-1-ol on oxidation with acidified or alkaline potassium permanganate gives 2-methyl-butanoic acid. Aldehydes can also be oxidized to the corresponding carboxylic acids, even with mild oxidizing agents such as Tollens reagent or Felling's reagent. For example, acetaldehyde is oxidized to acetic acid in the presence of Tollens or Felling's reagent. Ketones also give carboxylic acids on oxidation. However, ketones are oxidized only under vigorous conditions, such as strong oxidizing agents and elevated temperatures. Under these conditions, ketones form a mixture of carboxylic acids with a fewer number of carbon atoms, as shown here. For example, butanone, on oxidation with hot concentrated nitric acid, gives a mixture of propanoic acid and methanoic acid. One of the most useful methods of preparing an aromatic carboxylic acid is the oxidation of an alkyl benzene. Chromic acid or acidic or alkaline potassium permanganate is generally used for this purpose. It must be noted that irrespective of the length of the side chain, the alkyl group is entirely oxidized into a carboxyl group. For example, toluene or ethylbenzene, on oxidation with acidic potassium permanganate, gives benzoic acid. It is important to note that only primary and secondary alkyl groups are oxidized into a COOH group, while tertiary alkyl groups remain unaffected. For example, N-propylbenzene and isopropylbenzene are oxidized to benzoic acid in the presence of chromic acid or acidic or alkaline potassium permanganate, while tertiary butylbenzene undergoes no change under these conditions. In the presence of these oxidizing agents, even suitably substituted alkenes are oxidized to carboxylic acids. For example, but-2-ene, on oxidation in the presence of acidified potassium permanganate, gives ethanoic acid. Cycloalkenes, on the other hand, are oxidized to dioic acids under these conditions. For example, cyclohexene, on heating with acidified potassium permanganate, undergoes oxidation to adipic acid or hexane 1,6-dioic acid. The carbonation of Grignard reagents is another important method for the preparation of carboxylic acids. Grignard reagents react with carbon dioxide to form the magnesium salts of carboxylic acids. The free acid can be obtained from the salt by treating it with mineral acids. Grignard reagents can be obtained by the reaction of alkyl halides with magnesium metal in dry ether. The conversion of trimethyl acetic acid from tertiary butyl chloride is illustrated here. Did you notice that the acid formed by this method contains one more carbon atom than the alkyl halide? Thus, this method has the special advantage of increasing the length of a carbon chain. Hydrolysis of nitriles is another method for preparing the carboxylic acids. Nitriles, on boiling with aqueous alkali or acid, get hydrolyzed to the respective carboxylic acids. Aliphatic nitriles can be prepared by treating an alkyl halide with sodium cyanide in the presence of the solvent dimethyl sulfoxide. The synthesis of pentanoic acid from N-butyl bromide shown here illustrates the complete method. Note that the acids produced from the alkyl halide also contain one carbon atom more than the original alkyl halide. The hydrolysis of acid derivatives such as amides, acid chlorides, anhydrides, and esters yields carboxylic acids. Amides undergo hydrolysis on being boiled with a dilute acid or alkali. The hydrolysis yields carboxylic acid and an ammonium salt with an acid, and carboxylic acid and ammonia with an alkali. For example, acetamide, on being boiled with dilute HCl, undergoes hydrolysis to give acetic acid and ammonium chloride. On the other hand, when it is boiled with aqueous sodium hydroxide, it gives sodium acetate and ammonia. Acid chlorides, on hydrolysis, give carboxylic acids. For example, acetyl chloride, on hydrolysis in presence of water, gives acetic acid and hydrochloric acid. The hydrolysis of acid chlorides occurs readily in presence of an alkali. Hydrolysis in the presence of an alkali first yields carboxylate ions, which on acidification give the corresponding carboxylic acids. For example, when acetyl chloride is hydrolyzed with an alkali, it first yields acetate ions, which give acetic acid on acidification. Anhydrides give the corresponding acids on hydrolysis. For example, acetic anhydride gives acetic acid. Acid hydrolysis of esters directly gives the carboxylic acids concerned. For example, ethyl acetate, on boiling with a dilute acid, gives acetic acid and ethyl alcohol. Alkaline hydrolysis of esters, on the other hand, first results in the formation of carboxylates, which on acidification gives the corresponding carboxylic acid. For example, on boiling with aqueous sodium hydroxide, ethyl benzoate gives sodium benzoate and ethyl alcohol. Acidification of sodium benzoate gives benzoic acid. Having learned the different methods of preparation of carboxylic acids, now try to accomplish the following transformations. Benzyl chloride into phenyl acetic acid. Orthobromotoluene into orthobromobenzoic acid. Tertiary pentyl chloride into ethyl dimethyl acetic acid. The conversion of benzyl chloride into phenyl acetic acid involves an increase of one carbon atom. The conversion can be achieved by first treating benzyl chloride with sodium cyanide to yield phenyl acetonitrile, followed by hydrolysis with aqueous acid. This is a simple reaction of oxidation of the alkyl group. This can be achieved by the oxidation of orthobromotoluene in the presence of alkaline potassium permanganate. The conversion of tertiary pentyl chloride into ethyl dimethyl acetic acid also involves an increase in the carbon chain. This can be achieved by first treating the tertiary pentyl chloride with magnesium to yield the corresponding Grignard reagent. The Grignard reagent, on reaction with carbon dioxide followed by acid hydrolysis, gives ethyl dimethyl acetic acid.